Hello, my name is John Graham and I'm here to provide an introduction to the Gtilt Plus slope inclinometer software. A slope inclinometer is a wheeled instrument. It looks like this. Here are the wheels. This is the body of the instrument. The wheelbase is typically 500 millimeters, although some models have a 2-foot wheelbase. The instrument is inserted into a grooved plastic casing and lowered to the bottom. 2 passes are used for each data set. The casing has 2 A grooves and 2 B grooves. Only the A grooves are used. On the first pass, the tool face is in the A0 direction. The probe is carefully positioned at the correct depth and a reading is taken. Then the probe is raised 500 millimeters for the next reading. The probe gives a reading proportional to the sine of its angle of inclination from vertical. The reading is positive when the tilt is in the tool face direction. Most probes are usable in the range of -30 to +30 degrees. This is the kind of arrangement you usually see near the surface. You have a casing that's grouted into a hole. It sticks up perhaps half a meter or so. You lower the probe down to the bottom of the casing and take readings on the way up. You use the cable marks to make sure you take readings at a consistent depth from one survey to the next. At some suitable time interval, you come back and resurvey the casing, making sure to take the readings at the same depths as before. Each survey results in 4 inclination readings at each depth. So you end up with a series of data sets like these. Generally, each set is taken on a different date. What we're looking at here is the cumulative displacement plot in the A and B directions. Each of these plots represents the change in position since the initial data set was taken. In this case, the initial data set was taken on the 1st of June. And each of these plots has a later date. If I press F5, I can plot those surveys sequentially, so we can see that things are creeping slowly along over the course of several years. These plots are based on the assumption that the bottom of the casing doesn't move. It's also possible to plot assuming the top doesn't move, or to have the top move based on a series of surface surveys. But in most cases, the assumption is that the bottom doesn't move. You can see that there are 2 movement zones here. Let's see if we can visualize the displacement across those 2 zones. So we select Edit, Scales, and we can see that this lower zone is between 20 and 22 meter depth. So let's plot the 20 meter depth relative to the 22 meter depth. At the same time, there's another zone here. So let's plot the 8 meter depth relative to the 10 meter depth. So 8 meters and 10 meters. Now we hit Close. You see these little brackets appear to remind you which depth intervals you chose for the displacement time plots. We go up to the plot type graph here and we hit displacement time. This will just be for the A direction. This shows the 2 depth intervals and the displacement that's going on. We can change the scale here. We don't really need to start at -20. We can start at 0. Just type 0 in the box and press the Tab key. And we could use a full-scale displacement of perhaps 30 millimeters. You can make the scale whatever you like, really. Of course, there's also a B plot, which also has displacements that in this case happen to be about the same magnitude. It would be useful to combine these 2 into a single plot. They come out separately here because the displacement is occurring on a direction somewhere between A and B. Let me just remind you that the A direction is the direction of the tool face for the first pass. For the second pass, the tool face is in the opposite direction. You take readings with the tool face pointed in the A direction, and then you withdraw the probe from the casing, turn it around so that the tool face is in the opposite direction, and make another pass. Each pass starts from the bottom and works its way up, one depth interval at a time. Don't make the mistake of using the B grooves. It helps if you mark the A direction by cutting a notch in the casing. In order to get all of the displacement on one graph, it's useful to define directions X and Y, which are rotated clockwise from A and B by an amount known as the skew angle. But how do you figure out which skew angle to use? Here's how. Go to the main header and enter a small skew angle such as 5 degrees. That will make sure all the plot types appear, including the ones in the X and Y directions. Then you pick cumulative displacement X and Y, and you get a slightly different plot because this is skewed 5 degrees. You can interactively adjust the skew by pulling up the main header. Move it over to the left so it's out of the way, and increment the skew by 5 degrees repeatedly until there's almost no displacement in the Y direction. That gives us a skew of 40 degrees. You'll notice now that nearly all of the displacement is in the X direction and almost none of it is in the Y direction. I'll just close the main header. Now if we go to displacement time, A only, we have more displacement now because almost all the displacement is now in the X direction. Let's have a look at the Y direction and see what it gives us here. Displacement slash time Y only. See, there's hardly anything here. Let's go back to the X direction. Okay, so this effectively is giving us a measure of how the displacement over those two zones gradually increased over a period of about 7 years. I'll just go back now to the cumulative displacement A and B plot. If you want to see the individual readings, you can go to Edit, Readings, and we can open this window a bit farther if we want. You can see here the checksum plots, and these are the individual readings. So you can see here, for example, negative 368 plus 376 equals 8. And for any given depth, the sum of the A0 and A180 readings should equal the current zero offset of the A sensor. Similarly, B0 plus B180 will reflect the zero offset of the B accelerometer. They're relatively constant in this case, although this is not particularly wonderful data, but it's very usable and typical for its time. The instruments weren't quite as good back in 1994. We can go back and look at earlier data sets just by hitting Previous Set. They're quite similar. You'll notice there's one here that has a rather different mean checksum of negative 59. That's why that looks a bit different, but the data would still be okay. As you navigate through the readings, you'll notice that as the focus moves up and down the tabulation grid, there's an indicator, a sort of dumbbell, that shows you which readings relate to which parts of the plot. So you can see here that these readings are particularly important when it comes to creating this movement zone. What we're looking at here are the individual readings. but we can also have it display the change from the previous flag data set. The grid turns yellow to remind you that you're looking at the delta, the change from the previous data set. You can see that the main movement is in this area, and over the rest of the profile, the changes are not really that great. There are changes down here, but they're associated with the lower movement zone. It's through the readings editor that a lot of the specialized tools associated with Gtilt Plus are accessed. There are many specialized corrections that can be applied here, and I'm not going to go into all of them now. Some important ones are out of groove correction and settlement estimation, which leads to settlement correction. Let's get back to the regular interface and look at a few things there. You can see that these data sets are numbered 1, 2, 6, 7, and then 9, 10. That's because not every data set is being shown here. If I select the Manage Database menu, you can see that there's a little star here. The first starred set is used as the initial one. Only sets with a star are used for plots against depth or elevation. If there's a T in this column, that denotes a set that's included only on plots versus time. The starred sets also appear on plots against time. I'll mark a few sets to appear on time plots so you get the idea. In fact, if I mark all except the ones that are already starred, that will put all of them onto the displacement time plots. Of course, adding these will make no difference to the currently displayed cumulative displacement plot because it's not against time, but it will make the displacement time plot a bit more populated. You'll see there are a few more points on here than there were before. Back on the CD plot, pressing F5 makes the plots appear one by one. Holding down F5 gives you a kind of animation so that you can watch the displacements develop. I think the most useful plots for reports are the cumulative displacement A and B plots and the displacement versus time X only plot. If you want to flag all of the plots, and you have quite a lot of them, you can select Flag All. You might find the plot gets a bit too crowded, so if you don't like that, you can go to Set, Preferences, turn off the symbols on the plots, and now you just have lines for each one. You can still tell which is which, especially if you press F5. If you want to show stratigraphy on the plots, you can use the drawing tools. I could draw a line on here. And then add a little bit of text. I'll call it Zone 1. Firm lacustrine clay. And you'll notice it shows on both sides. And if you think that text is a bit too small, you can go to Edit Stratigraphy and select the text, increase it a couple of sizes, and it'll get a bit bigger. There we go. And when you hit File, Save, the stratigraphy is saved in the GTL file along with all the data sets. There's room for thousands of data sets if you want. When it's time to add more data to an existing GTL file, you start obviously with the GTL file, then you go to File, Import, pick whichever kind of data it is that you've got and bring it in. Normally it will just be a single data set with the latest survey. The new set will add itself to the end of this list, and you can pick Edit Readings and see the latest readings. You can evaluate the checksums here to see how good the quality is. You can see how good the plot is, and evaluate it in the context of the data you already have for this inclinometer. Once you're happy that you've imported the new dataset correctly, you simply hit File, Save, and it's in there along with all the other data. This has been an introduction to Gtilt Plus slope inclinometer software. Thank you for watching.